Okay, so do you have any questions for the paper that I share with you? This is the SciCon paper, right? Today we are gonna go in more details on how to derive the necessary optimality conditions for the discrete approximation problem. So we will go back to the discrete problem first, okay? Let's start from this one. Okay, maybe I should write in the good notes or somewhere, and then you can see the, oh, okay, I'll just show the screen here, and then after that, like whenever we need the computations, I'm gonna write on the screen. Is that okay, everyone? Can you see the screen?
Yeah,
This
yeah,
is
that's
the
okay.
problem. Yeah, this is the problem PM, right? And then this is the discrete approximation problem from the continuous problem. Let me recall what is the continuous problem. So in the continuous problem, we need to minimize the cost functional, that is phi of xt, because in the previous meeting I already mentioned the meaning of this problem of the sweeping processes and the big picture in some applications already. Today we're gonna go to the details of the paper. The cost functional here, it is, this one is called the terminal cost, and we have x here is the state variable, t here is the final time. So in the real life, this can be the distance, right, from A to B, or it can be the number of the drugs in some applications, like in biology, or maybe it can be um, uh, the beam delivery time in when you want to detect the tumor in brain cancer. And we have the dynamical systems here, where the set C here is a convex polyhedron, and this is the fixed set. So it is given in this form. It is a fixed set, so this xj star and cj here, they are given. And norm of xj star is 1 because we normalize it already. And this is just the normal con definition, right? Okay, we have some constraints. This is the hidden constraint to make sure that we have the normal con. It's not like it will not disappear because x belongs to c. And then we have some other constraints related to the control is little u belongs to the set capital U. Now we will try to construct the discrete approximation problem by using Euler explicit scheme. We will approximate the derivative by xt plus h minus x of t divided by h. And we have the discrete mesh. So we divided the interval from 0 to capital T into all the smaller subintervals, T0, M, T1M, and then T2MM. Because in this case, if m approaches infinity, you can see like all these intervals, they are very getting smaller and smaller. In the discrete approximation problem, we become the continuous problem, will approximate to the continuous problem, and then we can get the convergence. And also we discretize the dynamical system. Actually, for this one, let me write on the screen. By the way, please feel free to stop me anytime if you have any question, okay? I'm gonna write on the screen. This one, you have, let me change another color. Xi plus 1 divided minus xi divided by, I will not write m because we understand that there will be the m for the index. Okay, I'm gonna write here, but anyway, belongs to capital F of x I m u I m. And then this term, it is exactly the derivative term, right? This is the derivative of x dot belongs to capital F. And you remember that capital F here is the normal con minus the perturbation. So basically that is exactly like negative x dot belongs to capital F, right? Do you agree with me, everyone? So this one is equivalent to this. I'm gonna move down, so maybe I'll erase that one later. Uh, let me clear this. Wow, it doesn't work. And the first theorem, actually, I'm gonna just mention the meaning of this first theorem, but I'm gonna skip it because for the first theorem, I'm gonna prefer to use another paper instead of this paper. Basically, for the first theorem, we need to verify that the solution exists for the continuous problem and the solution will exist for the discrete approximation problem as well. After that, we will construct the discrete approximation by this way. So for the cost functional, instead of x and u, you have xm and um, right? For the terminal cost, you have x. Instead of x, you just replace x by xm. Instead of u, you replace it by um. And then for the running cost, you add this term because when m approaches infinity, this term goes to zero and this term goes to zero. So that's why the tail here goes to zero and it approaches our original cost functional, right? And similarly, you can derive the dynamical system. This is a new one. And this is the constraint. Actually, when you have xt belongs to c, then it satisfies the formula of C. So in the formula of C is xj star x less than or equal to cj, right? So we discretize it, everything here. Actually, right here, it should be im, but the thing is, since there is some trouble later on, so that's why we just consider it at the point x at the time t 2m instead of tim. So that one way, when you do it in more details, you will see it later. And now we can skip that details. And then for the continuous, no, for the inequality, we will have this inequality as well. Since Sm approaches infinity, this one goes to zero, this one goes to zero. So this is one of the constraints that we need to add to make sure that the tails goes to zero. And the constraint related to the control variable u belongs to the set capital U. We have we replace u by uim, right? It's easy. So we are done for the problem PM. Uh, okay, because you are gonna watch the video again, so maybe I'm gonna go ahead and move to the discrete, move to the step deriving the necessary optimal leading condition, because that is the main step. Okay, here this section 6. So for the section 6 here, we take x m bar. Whenever you see the bar here, it is the optimal solution, right? The optimal solution for the problem PM, because it is the discrete form. It is in the discrete form, not the continuous form. And for xm, you know that it belongs to when you discretize it, let me see, it's gonna be this number is gonna be x0 x bar of t0m, xm bar of t0m, and this one is gonna be x bar m, the value of x bar m at the time t2mm. Okay, and similarly for u, you have these are all the values. So each of them is belongs to R. It is a number. And this one, it is x bar m, and the whole thing right here, it is u bar m. Okay, I'm gonna clear this ones to make sure that we see the theorem. Is everything clear so far? Yeah, I'm
Yeah,
supposed
thank
it's
you.
gonna be clear. Yeah, if it's not gonna be clear, then you can ask me. Suppose in addition that the cost function phi is Lipschitz continuous, you can say this is phi or phi. Yeah, there are two ways to read it. Is phi is Lipschitz continuous around the point x bar m capital T, then there are elements, because I think last time I told Tang that you need to read KKT condition, because it is important when you study KKT condition, you can understand how do we derive necessary optimal Lie conditions for this problem, because it is going to be the generalized form of the KKT condition in finite dimensional space. For KKT, it's for finite dimensional space, right? Now we are working on infinite dimensional space, so that's why we need to study it for the finite dimensional first, and then we generalize it. Now, when you have the optimal solution, we need to derive necessary optimal Lie conditions. How can we derive it? I'm going to introduce a little bit about this equation. The first one is called a non-trivial Lie conditions. The second one, actually, it is from like the condition x t belongs to c. This condition, it is called the transversality conditions, and this is like it comes from the geometric constraint. It comes from the dynamical system, and this is just the definition, the new definition when you define the angle theta in the dynamical system. Okay, I'm gonna go to the details of the proof for this theorem. So we denote z. So in this case, z here can be written in terms of like, okay, we notice that x, right? X from x0m until x2m u here as well. But the reason that we have u until 2m minus 1 only, it is because u here is a measurable function, not the absolutely continuous function. So if you have the absolutely continuous function, you can consider it at the until the final time. But if you have the measurable function, or sometimes just the piecewise constant function, then you will have it up to m minus 1 only. And then u for y here, actually when you read the proof, you can see why here it plays the role as x dot, and when you have x dot, it goes up to 2m minus 1 only. It will not go to 2m. So the only one item it goes to 2m here is the state variable. I'm going to erase all the errors so that it's going to be clear for the next one. And this is just the dimension, right? We just calculate the dimension here. This is 2m plus 1. This is 2m and this is 2m. So you add them all together. But please remember that each element here is a vector, okay? It belongs to Rn. So that's why when you have 2m, 2 to the m numbers, and no, sorry, 2 to the m vectors, and each vector belongs to Rn. So the dimension of this one is going to be 2m plus 1 times n, right? So that's why you can do the calculation, and then you can add them up, and then you can get this dimension. And where the starting point x0m is fixed, because we are given x0m is the value of xm at the time t0m, right? And you know the initial at the initial time we already know the state value, so that's why it's fixed. And then we take epsilon greater than 0 from pm. Consider the problem of mathematical programming. MP is mathematical programming here with respect to the variable z. This is the new this is the cost functional in the mathematical programming problem. Actually, in this one, we just need to consider the terminal cost at the final time for x, right? I think there is a typo here. This should be xm, right? Not x. Sorry. Wow. It should be xm. And plus, this is the tail, right? This is the tail. So YIM, as I mentioned before, it plays the role as xm dot. So that's why you have xm dot minus x bar dot, because this is from the discrete problem. This is from the continuous problem. We will have the convergence. That's why when m goes to infinity, that subtraction, the whole difference goes to 0. and this one goes to 0, this one goes to 0. So that's why we edit the tails like that. And we considered all the new constraints. So the first constraint here, you can see we have ymn minus x bar dot uim minus u bar, right? And it is less than epsilon over 2. That means like ym here goes to x bar dot, sm approaches infinity, and uim goes to u bar, sm goes to infinity. And then for the second constraint, this is from the Euler scheme. When you always have this constraint, these constraints, okay? This is the first one, we always have it. And this one, we always have it because you have xim plus 1m minus xim divided by hm equals ym. So that's why you obtain this constraint. And then this constraint comes from xt belongs to c. Do you remember that? Because it satisfies the equations uh, of the formulation in the set C. And then after that, this constraint, it is called the geometric constraints. And you know that z belongs to this set, I will call it zeta I, and negative ym, because ym plays the role as x bar m dot, right? It belongs to capital Fm because that is like from our dynamical system earlier. And this constraint x0m is fixed, of course, because we know that it is given. And uim belongs to u. So these are all the constraints, and we put it into this form. So that is the mathematical programming problem, and we are done with the mathematical programming. So now we need to derive the necessary optimal leading conditions for the mathematical programming in terms of generalized differential tools reviewed above. You can look at the book. This is the book, the first book of Professor Boris Morokovich. You can look at the proposition 6.4 and theorem 6.5 in that book. It helps you to derive the necessary optimal leading condition for mathematical programming. So these are the two theorems needed for the NOC for the MP problem. NOC is necessary optimal leading conditions. I'm just saying it in a short form, and we specify them for the optimal solution in this way. So z bar, right? Z bar, as you can see, it comes from z here, but since it's the optimal solution, so you add the bar on the top of z, and then instead of all these elements, you just replace them by the notation with the bar. So they are all optimal solutions, right? Corresponding to the state right here. This is the optimal solution corresponding to the control variable, and this is the optimal solution corresponding to the x dot to the MP problem. So this is like for the mathematical programming problem, okay? And it follows from theorem 4.2. So theorem 4.2 in this paper, it is the convergence theorem. The convergence theorem, it says that, okay, I can go back so that you can see 4.2. It says that if you already have the let's say the local minimizer for the original problem, right? That is like the optimal solution for the original problem. Then you can always derive the piecewise linear function xm bar and the piecewise constant function um bar. This is the solution for the discrete approximation problem, and this is the continuous solution for the continuous problem. And then you have the strong convergence in the space W12 times L2, because X here is in W12 and U here is in the Lebesgue space. So that's why it's measurable, because it is a function in Lebesgue space, so it is measurable. And for the function in Sobolev space, you know that it must be in Lebesgue space firstly, right? And its derivative must be in the Lebesgue space as well. Now I'm gonna show you like on so that theorem, it is the convergence theorem, saying that the inequality constraints in the mathematical programming in the MP problem defined by phi is inactive for large M. What does that mean? That means like for the when you have the convergence, right? So for all the inequality right here. Oh, wait, why it doesn't work here? Mm, divide by phi. Okay, look at phi here. Oh, I cannot see right here. Why? 100%. Weird. I could not write on the. It's only. Can you see my pencil, everyone? You cannot see my pencil, right? It's weird.
No, I don't see any pencil.
Yeah, let me see why it worked earlier, but now it doesn't work anymore. Um, Apple Pencil, okay, connect. Okay, I'm gonna show you here using the mouse then. So for if you look at phi, right, the function phi, so the constraint, the inequality constraint divided by phi here, it is this inequality, the first. Oh well, it is the first inequality here. And when you have the theorem for virtue, that shows, okay, for the convergence, so why I am here approaches to x bar dot, and then we have u I m approaches to u bar. So that's why when you do the convergence, this difference will be less than epsilon over 2. And when we mention like the inequality constraint divided by that one is inactive, that means it will be inactive. So this constraint will gone, like, because it's satisfied, right? It is satisfied as m approaches infinity. So that's why it is inactive. It is not active. And it can be deduced from, this is the book. Sorry, I lost that one. And so the corresponding multiplier does not appear in the optimal ready conditions. I'm going to explain like this. So for the KKT, maybe I have to show the KKT condition. KKT condition. Why are they mentioning about the multiplier in the optimal ready conditions? The reason is when you minimize a cost function or subtract you the inequality and the equality constraints, right? You can see here, this is the Lagrangian function. You need to set the Lagrangian function equals 0 and solve for that. Do you agree with me? And then the first term will be the cost function over here. The second term will be the inequality. This is the inequality on one side multiplied by the multiplier mu t. And then we will get another function for the equality constraint multiplied by the multiplier. So mu and lambda here are called multipliers, and it goes together with all the constraints. But when the constraint is inactive, like this, for example, if this inequality is inactive, so it's gone, so we don't have this term, and that's why we don't have the multiplier as well. And that's the reason why they are mentioning like the corresponding multiplier does not appear in the optimal ready condition. And we can find lambda m greater than or equal to 0. This is Cm. Cm belongs to Rs plus, that means like all these numbers, they are in the first number, it is in R and it's positive. So it's different from 0 as well. And P here, it is also one of the multipliers. I'm gonna explain it later here. Please remember, this is a vector and this is also a vector, okay? And this is a number. The reason uh, the reason is as follows. When you consider zi star, this zi star, so what is this? This is from the dual problems. We can find all these elements in another vector in the dual elements. It is similar to the one right here. So you can find all the dual elements mu lambda. You can find you can find let me Okay, this is the dual problems for the necessary conditions. Then there exists a constant here. There exists a constant mu and lambda satisfying the following thing. Zero must be will belongs to the subdifferential of f plus like or the multiplier or multiply by the you can understand like if these are smooth functions, so this this notation becomes the gradient, okay? But if because they write in the general form where f here can be the non-smooth function, h here can be the non-smooth function, and g can be the non-smooth function. So that's why they use this notation for the non-smooth functions. And normally for the finite dimensional space, you have zero equals this term. And the left hand side here will be a number, and the right hand side here will be zero. So that's why we have the equality. But in this case, since the left hand side is zero, which is a number, but the right hand side here it is going to be a set because we have the subdifferential of the of these functions. So that's why it's going to be a set. So a point belongs to a set, and then we will solve for that. So we will find the uh, z star here. This is the solution for the dual problems, which are not zero simultaneously. That means like all these elements, they cannot be zero at the same time, okay? While satisfying the conditions. These are the conditions that comes from proposition 6.4 and theorem 6.5. You can see it in the book here, okay? But now you can understand that we pick this number belongs to normal con to the set to these two sets. So we will take the two sets from the constraints zeta and omega, and then we will add them. If I belongs to the set the index set from 0 to 2 to the m minus 1, and then for the final time where I equals 2 to the m, we just have the normal con of zeta only. We don't have omega. The reason is if you look at the this constraint, you just have I up to 2 to the m minus 1, right? But if you look at zeta I here, it goes up to the m 2 to the m minus 1, but there is one more. This is also from the set zeta, but I goes to 2 to the m. So this is for the final time. So that's why we combine them here, and then we separate the other one right here. And then this is also like one of the constraints that is deduced from proposition 6.4 and theorem 6.5 in the book as well. We have negative z dot 0 minus until like z star 2 to the mth belongs to, okay, so now let's see, this is the KKT condition here, because lambda here it goes with the grade the let's say partial derivative of phi no subdifferential of phi 0 of z bar, right? Plus because this function we don't know the smoothness or not, it is general, so that's why we use the subdifferential. And this function ha and gi here, they are smooth function. You can see here they are smooth functions, right? So that's why we use the gradient instead of the subgradient. And this is the multiplier that goes with the constraint, the multiplier that goes with the constraint. And then there's another multiplier that goes with the equality constraints. So it's going to be down here. Z, this is CJM times HA of Z bar equals 0.
Can you
Yeah.
explain for me what is Z star?
Z star here, right? Z star here is the solution for the dual problem. Like, for example, in the continuous
So
problems, you
it's
have Z,
a
right?
set of
Z
it's
here
a
is
set
here.
um, it's a set of lambda and mu, right?
No. So Z here, it is the vector of this form, right? it is in the continuous problem. Z bar, it is also like you can see the same form, but this one is for the mathematical programming problem above here. And Z bar here, Z star here, it is, it has the same form as well, but it is in the dual problem. And this number and these elements, they cannot be zero simultaneously. So that's what they meant. And for Z star I here, it has the form right here, and it be for each for example, X star I 0 I here, it is in Rn, and this one it is in Rn as well. This one is in Rn, this one is in Rn, this one is in Rn. Yeah, each of them is in Rn. So this is like if I draw the picture, let me see if I can show good notes. I can try. When I calculated it, I have to draw it like this. The host can share this meeting. Maybe let me make myself co-host. 1 second, please. With the chat, the participants. Okay, make the iPad become the co-host so that I can share the screen here. Or anyway, I can try to, because I'm afraid that I don't have enough space here to write it. But if I move that is okay. So X, oh, I cannot see right on my iPad. I don't know why it works well earlier, but now like it doesn't work. Maybe let me change you the new. Let me change you another Apple Pencil. Let's see if this one looks better. Sometimes I have to restart it. It's just like, oh, this is 0%. I think the problem is not with the pencil. The problem is with the iPad. I have to restart the iPad somehow. Maybe because I have been using it like more times today, so that's why now it doesn't work. Weird, very weird. Never happened. I can do like this. Let me stop sharing and I'm gonna share it again just to see if it works. Oh, now it works. Oh wow. So I have to stop sharing and share it again. Now it works. Z star I, right? It is in this form. OI until X star QMI and so on, so on. We have the tail as well. But for each star 0I here, okay, wait, how do we find these elements? If you have x0m, x0m, this one is going to be different, because if you look at the index for the index down here 0I, instead of like for this one we just have one index at the bottom, right? X0m. So for x0m it will be, it is in Rn. It's in Rn. I should use 0I. The reason is because we have the star on the top already, so that's why we could not, we don't want to mess up with the star. That's why we move the other index down there. Actually it should be I, it should be I0, I0. Okay, I see, I got it. So this one, it should be star 0, I here will be 0, 0, because I runs from 0 to 2m, right? I'm gonna write 0, 1, 0, 2 until x star of 0, 2 to the m. And then for, and then you can keep writing it for x star 0, no, x star 1, 1i, right? Because this is x star 0i, then the next number will be x star 1i, and then the next number will be x star 2i. So you have to keep writing it. X star 1i, it's going to be 1, 0, x star 1, 1 until x star 1, 2 mth. Right? This is not difficult. It's just like it's going to be a mess with all the notations. And then for the last one, it's going to be a vector as well. Please remember I here runs from 0 to 2 to the mth. So you have x star 2m0 until x star 2m 2m. That's how we write it. And similarly for u here as well and y here as well. Are we good?
Yeah,
And
we're good.
yeah, and then this is x bar 0m. You can also write in this form. So it's going to be a very long vector like that. Clear all my drawing. Okay. I just want to explain that carefully, and then now I'm gonna move to the next one. So we have know that the first line in 6.6 comes by applying the normal cone intersection formula from this is based on what I remember. Oh, this is the book as well. This is the book, but the corollary 3.5 use that x z bar belongs to the intersection of these two sets, zeta i and omega i, where I runs from 0 to 2m minus 1. This is just the first part, the first line of 6.6. And if you want to, if you want to apply this corollary 3.5 from the book, you have to prove the qualification conditions. That means the intersection of these two normal cones is 0. It contains only one element, 0. And it follows directly from the co-derivative estimate 5.6 of theorem 5.1. Yeah. For this theorem, for this part, actually, this is gonna be separated. So I'm going to uh, I'm gonna discuss this question later with you because it takes like a page to explain this inequality, actually 1 page. And today I don't want to I want to skip this one for now, so that please just understand how we got this one, and then maybe in the next meeting I'm going to explain how to verify the qualification conditions. It is very important because this is the qualification condition here is the assumption in this corollary corollary. So that's why if you want to use this corollary this corollary, you have to prove the assumptions, that is the qualification conditions here. And let me see the co-derivative estimate. Okay, and this one, it helps you to prove the qualification conditions. So we can skip this one for now. In next meeting, I'm gonna I'm gonna show you theorem 5.1 and the co-derivative estimate and also the verification of the qualification conditions. But this one, it shouldn't be the issue for this paper. And then we deduce from the structure of omega I and zeta I that the inclusion in 6.6 can be equivalently written as this form. Okay, how do we rewrite in this form? It is because when it satisfies the qualification condition and we apply the corollary here, we can arrive at the following inclusion 6.8. So in 6.8, you have x star I u star I minus this term negative y star I belongs to the normal cone here. And I think for the explanation, it takes time to explain this one as well. It's not obvious. This one and this one, they are not obvious. When we write the original paper, actually it takes like 1 page or 2 pages to verify this one. But for Scion, for the publication in Scion, they have the limitation of the page is 30 pages. So that's why Boris like removed all the proofs for those part, and then he just verified that, he just mentioned that okay, it is verified. And that's why it creates a lot of trouble for us when we do the review, when it goes through the review, because the reviewer doesn't understand this one and we have to like send them the proof like separately. Now we observe that, let's skip this step, I'm going to explain it later. That one belongs to the above. Observe furthermore that this number and this number determined by the normal cone zeta 2m are the only non-zero components of this one. So when you write down z star 2m, you can go back to z star I here, and you replace I here by 2m, right? So if you replace I by 2m, then this one is gonna be, we just have one element, x star 2m. So right here it's going to be 2m, so that is a vector in Rn. And similarly for u and y, and then you can rewrite that one belongs to this normal cone plus normal cone. And then since these two elements are the only non-zero components of the left hand side, so that's why for the right hand side, we can this one. That's why other numbers are gonna be zeros. The reason is we have to write carefully. Okay, let me z star I. Okay, z star I, I'm gonna write it. We wrote it earlier, right? It's very long. That's why I'm very lazy with all the calculations here. When I did it, I write it like it looks like a mess, but z star 2m, z star 2m. So we do it carefully. This one, it requires the careful step. Oh, again. Z star 2m is gonna be x star 0 2m x star 2m u star 0 2m u star 2m minus 1 2m y star 0 2m y star 1 2m y star 2m minus 1 2m. This one for sure is not difficult. It's just like it takes time in the notation. It looks ugly. Z star 2m. Okay, z star 2m belongs to, remember, look at 6.6, the second line right here, when I equals 2m, right? So this one belongs to the normal cone of z bar Z bar, we have to write Z bar. Like please write carefully like that. Then you understand everything in more details. I'm gonna write Z. This is X bar Q M M U bar 0M U bar Q M minus 1M Y 0M Y Q M minus 1M, right? So this is Z bar of theta I. Okay, so now theta I, it is going to be the set that contains this element. And look at this element. It has the property right here. So what I'm going to write here is I'm going to write out the set carefully, all the data in that set. QM. When I did this calculation, I write all the details out, right? I will write them explicitly, not implicitly like this, not dot dot dot, but I write out all the elements there in between. Whenever it is related to the constraint, I'm going to write it down. For example, if you look at the this element, if we want to make sure that it belongs to the normal cone to this set, right? And let's consider maybe if you separate them in terms of like one element, this element belongs to normal cone to the set to the set at the point x bar 0M. Then let's look at x bar x 0M is satisfied. Look at the property of the set related to the first element. So in the first element, look at this one. It is when you have 0, I equals 0, right? I equals 0, then I equals 0 here. So this is the constraint related to negative x dot 0M belongs to the normal cone. This one, you can rewrite it explicitly. It's going to be the normal cone minus g, right? The function g. And when we have the, and there is a tip for you, because when I do a lot of calculations, I notice this one. So it helps us to reduce the time of the computation here. If in the constraint here, we have x0, x dot 0M belongs to something, that means there is some constraint for the set omega here for that first element. And whenever you see the constraints, then you have to make sure that this number, it must be 0, because 0 belongs to because you can imagine, like when we have the very strict assumptions, and if you want to make sure that an element belongs to that one, that uh, that element will be 0. Will be, let me check it real quick. So these are only non-zero components. So x0 to m, this one will be the non-zero components, and this one will be the non-zero components of z star to m. So these are two non-zero components, and other numbers are zeros. The reason is wait, we just have two non-zero components here. Other numbers are going to be zero. I see, because this one is 2 to the mth. Let me go down. Okay, 2 to the mth, only 2 to the mth. So the constraint is with I equals 2 to the mth. I see. I was incorrect. I look at this set, it is incorrect. I have to look at this set, okay? Because this set is for zeta 2m, not this set. This set for I equals 0 to 2m minus 1. I have to look at this set. So when I look at this set, I can see x0m is fixed. There is another typo here. Wow. We check it many times and still have typo. This one, it should have x0m is fixed and u0m is fixed, because whatever you have in the constraint in the set, then it will make the set like it's gonna be smaller and it has more restrictions. And if it has more restriction and this number wants to belongs to the normal con to this point to this set at the point right here, then these elements must be non-zero. In that case, we will have the constraint for these elements, and other elements they are zeros. So if you look at the constraints, right, whenever you see the constraint right here, then the element corresponding to z star, it will be non-zero. That is a tip after I do a lot of computations. Like, for example, I will do one computation for you here. Maybe I will separate the first element only. If I separate maybe x, oh, wait, it happened again. Okay, so for the first components belongs to normal con x bar 0m, and then this one, if I write an element in this set, is gonna be x0m, where x0m satisfying the following. x0m is fixed. x0m is fixed. No, it must belong to the set. This is a set. And if you want to rewrite, assume that this set is convex, okay? Convex, then based on the definition of normal con, what do we have? We have based on the definition of normal con, okay, let me show you. If you have, I can go back and then I can show you the convex one right here. This is the place where you should see. So if it belongs to the normal con, and assume that the normal con is convex, so any element in that normal con, we have the inner product with this vector less than or equal to 0, right? I'm going to rewrite here. So there will be a vector v in the normal con. So whatever vector in this normal con, that is x star 0 2 to the mth times y minus x. Y is in C, so the element in this set is going to be 0m, x0m minus x bar 0m less than or equal to 0 for all x0m in the set zeta 2 to the m. That's how I do it. I write everything carefully in more details like this. And for this term, when I write less than or equal to 0, I will have, let's look at this one. It is fixed, so this term is fixed. And let me use another color, the blue color. Since this is fixed, if you want to make sure that this inequality less than or equal to 0, then what do we have, everyone? What do you think? Then this one must be, let me go down here so that you can see the conclusions. x star 0 to m are the only non-zero components, because because we have the constraint for this. We have the constraint for this. So if you want to make sure that this constraint satisfies, so this one must be non-zero here, and it should satisfy this inequality. If this one is zero, oh wow, if this one is zero, then it's obviously like equals zero. So if it equals zero, then what do you know what happens? Because I'm trying to prove by contradiction here. If this one is zero, then this inequality always whole. And if it is always whole, so this can be whatever number and it will not be fixed anymore. So that's why we have the contradiction here. And when you have the contradiction, that's why you can make the conclusion that x star 0 to m here is the non-zero component. So that's why we have this step. Okay. Um, yeah, and then when I continue to do all these calculations, similar calculations, I will also have like u dot u star 0 to m is the only non-zero components as well. So let me erase everything here, right? And we can then clear all my drawing. Okay, and then I can continue to explain the next thing. 6.6 and 6.7 implies this one. The reason is, okay, so 6.6 and 6.7, this is this is right here, the middle part here. I'm just rewriting everything, right? You can see everything will be rewrite here. And then with eta times this one equals 0, because that one it comes from the 6.7, because HA here is exactly this one. This is HA. Can you see my, yeah, the screen? Okay, this is HA times C equals 0. Using the expressions for phi 0, GI, HJ above together with the elementary subdifferential sum rule. So the sum rule, the subdifferential sum rule, that means when you have the subdifferential of f plus g, it gives you subdifferential of f plus subdifferential of g, but there will be some assumptions for the function f and g here. Okay, you can see the book for more details for this proposition. Now I'm gonna use the sum rule, chain rule, and composition and everything, and we can apply it here. Now let's do the calculation. Actually, let me tell you a very funny thing. When I did this paper, I calculated everything by myself. But now when I tested it with ChatGPT plus, like ChatGPT education, I think in is in SDSU, so you have ChatGPT education. You can, last time I edit all these assumptions above here. I put it, I told them to save it in the data. And then after that, I tell them to calculate this term, and it gives me exact answer already. I was like, it takes time for me to calculate all these things, and now like ChatGPT can calculate everything for all these steps. But still, there are some errors, little small errors, but we can fix it by ourselves when we tell them to derive like the calculation step by step, and then you can check all the calculations. You can test it. It is very nice. I'm not sure if in Thanks University do you have like ChatGPT free?
I don't know. I don't think so.
I see. Yeah, maybe I can share because I have ChatGPT education for free from SDSU, but I'm using my grant to buy ChatGPT Plus as well. But ChatGPT Plus, like right now, I'm not using it. So if you need it, maybe in the future, if you want to do like calculation, you can let me know. I can give you the account and password, and you can
Yeah,
use it.
that's great.
Yeah.
Thank you.
Yeah. And then this one is the computation. We can do it step by step like this. This is the multiplier, right? This is the gradient of a function, and then whenever you calculate the gradient, you have to take the value with respect to x to m. So now I'm thinking like I want to show you in more details for the calculations, but and then after that I can show you like how ChatGPT did the calculations for me here. Maybe let me firstly show you the calculations I did by myself first. The sum CJM gradient of HJ bar J equals 1 to S. Okay, so now what about the gradient of HJ? So this is HJ, okay? Gradient, that means like similar to, okay, you take the derivative with respect to this variable. So you consider this one as a variable, right? So the constant in front of the variable, because with the inner product, it's gonna be like the multiplier. So you have this term for the gradient. Um, and remember, please try to let me try to write in more detail so that you can see it, because I shouldn't skip step. If I skip step, you will not understand everything in more details. Okay. Here, what I'm gonna suggest you to do is you will need to write everything in more details. For example, this is the sum, right? So the sum when J runs from 1 to S. So let's write in more detail like C1 M times gradient of H1 Z bar plus C2 M gradient of H2 Z bar, right? Plus until like C S M gradient of HS Z bar. You do it step by step like that, and then you will find all uh, the 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 constant terms that go, or maybe you can find all the terms that go together with x to mm, and that's gonna be this form for sure. For example, I will do it like this. This is eta 1m, right? Eta 1m, if you have eta 1m times the gradient of h1. So if you have h1, replace j here by 1. I will replace j by 1, and then you can see here. If I replace j by 1, so the term in front of x2mm is going to be these two numbers, right? So it's going to be c1m z1 2m m. And similarly, for the second term right here, you can do it similarly, c2m z2 2m m. And then wait, this is a type, there is a typo right here. Did you notice that? This is, it must be xj star right here instead of z. This is the typo right here. Please notice that, okay? This is xj star, and then right here it must be x1 star. This is x2 star. Do you agree with me? And so on. So you have C S M X S star. So that's why you can rewrite it as the sum right here. So that's how you can calculate the left hand side. Okay, so now I'm gonna erase all the calculations here. And similarly, you can do it with this one. Just try to write out it in more details. Like for sure, you can calculate all these things. Very easy. This step is easy, just calculation, write in more details. And if you have any questions, you can ask me. Maybe I can help you with the first one here, okay? Do you need help with that one, or maybe you can do it yourself? Just try to do it similar to the first calculation that I did, And if you have any trouble, maybe I can explain it in the next meeting then. And then for the next line, this is the subgradient of phi 0. It equals this one plus this one. Okay, I'm gonna go back to how can I go back and you still see that? Okay, maybe you try to remember it. This one, okay, phi 0. This is the terminal cost at the final time. This is 2m, not m. There's a typo here. And then this is rho I. Rho I here is just the integral of this term minus this term. This is 2m. Okay, I'm gonna go back here so that you can see phi 0. It is gonna be the sub differential, right? Plus this is, it is like a smooth function, so you can take the gradient. You can take the gradient. So this one is easy as well. And then the set lambda m times this one above is represented as the collection of. So this one you have to write down carefully all the terms inside here and then rewrite in the collection of this one. Let me erase everything and then I can try to write down carefully. Okay, now let's try to write this one. Lambda m times this one, lambda m multiplied by this. So the first term, please remember that this one is has the form of z bar. Okay, so this corresponding to x bar 0m. This one, it corresponds to x0 2mm, 2m minus 1, sorry. And the last one here, x bar 2mm. And similarly, for this one, it corresponding to u bar, and this one to y. Y is it plays the role as x bar dot. Okay, let me clear this one first, and then I can zoom in a little bit. Okay, why do we have 0 here now? Why do we have 0? Why do we have 0 here? Lambda m. Theta here is gonna be this integral, Um, 1 second, let me, I have a message real quick. Important one, so. Okay, so let me get back. Yeah, I just yeah, I had like 2 meetings, like 3 meetings, consecutive meetings today, so I'm a bit exhausted now. Let me try to think about this. Mm, do you have any ideas? Now I feel like my brain now is not working anymore. Let me see. Yeah, Uh, because what I'm trying to do is I want to explain this one and I want to explain this one and okay, yeah, I mean like I will try to explain this one and this one in the next meeting then, because if I'm done explanation for this one and this one, it's gonna be very easy, and then after that like you can try to rewrite everything by yourself. Maybe if you already have a headache, I think that I can stop the recording here and then and, and then like we can meet next time and then I'm gonna continue to record the rest part of the theorem. Is that good, everyone?
Yes, good.
Okay.
I
Yeah,
found it.
yeah. I mean like this one, when you study this, you're done with this one, you can write a paper immediately with this technique. Like every technique is has their own difficulty, so like we have to accept that one then trade off. um okay, let me stop recording first.